First of all, I would like to thank you, Dr. Mani, for your introduction, and thanks to the audience for attending this seminar. Is my voice clear now? Clear?
Yes, please go ahead.
Okay. So as the title says, I'll be talking about my PhD work in this seminar. As you can see, the PhD thesis about enhancements to the multipath transmission control protocol for Internet of Things wireless networks. This will be my outline in this presentation. I will be giving a little bit of introduction, followed by a literature review and the main three contributions. Finally, I'll be explaining the conclusion, limitation, and future works. In the past few decades, the internet has mainly been used for like exchange news, literature, entertainment, and gradually the internet has changed to include some connectivities like Internet of Things. There are some reasons, but the common ones are the internet speed is available everywhere. The second one, smart IoT devices widely available, including smartphones and all other stuff. The third reason is cloud-based information infrastructure is widely available, including cloud computing, cloud storage, and so forth. So what is IoT? In a basic form, it is a network of physical components like sensors, smartphones, etc. These things communicate together to achieve some functionality using the internet. Real-world example includes smart homes, vehicle communication, and health monitoring. In the literature, you might find that the IoT layers is given as 3 layers. But as a researcher, I personally go with the 3 layers perspective. So we have perception layer in the first line, and then network layer, and finally application layer. These are the layers of communication system of IoT. Perception layer, basically the sensors. Network layers could be routers, gateways, and some other devices. And application layer can be servers and even smartphones. The term of Internet of Things is first introduced in 1999 by Kevin Ashton. However, the concept of IoT was first discussed in 1989. So the term of Internet of Things is proposed in 1999, but the concept is used back in 1982. The first application of IoT device was Coca-Cola machine in Carnegie Mellon University. The concept of IoT has gone through some stages until 2013, where some companies started to produce some equipment and devices and being published. We might need to have a look to the network models in a quick. Here we have 2 well-known network models, the OSI and TCP/IP. Basically, the main difference is the application layer. Here in the right-hand side is only 1 layer here, where OSI has 3 layers instead of 1. Let's talk about the main theme of this thesis, multipath TCP, or some people say MPTCP. This protocol is an extension to the well-known protocol TCP, The main difference between those two protocols are the number of paths. So the best example to explain the concept of this protocol is smartphones, where most of the smartphones have two access to two different networks, probably Wi-Fi and 5G. So Multipath TCP uses those two networks, for example, to transmit a single data flow. So using this method gives telecommunication an advantage that the throughput will be increased and delay should be reduced. The protocol is a relatively new protocol, was published in 2013, and it basically contain several TCP connections. So the TCP connections in the multipath TCP called subflow. So when we say subflow, means single TCP connection. This is the outline of the architecture of the protocol. Application and network layer remain the same. Transport layer is divided into two layers. The upper one is the connection level, which is managed by Multipath TCP itself, and the lower layer is called the subflow layer. Basically, the number of paths or the number of TCP connections. If we have 5 packets here, then the protocol will split the packets into some of them will be sent on the left-hand side, and the rest will be sent through the right-hand side. Here is another example. If a device has multiple connection, one of the advantages of multipath TCP is to increase throughput. So if I have these packets, wanted to send it to the destination, some of the packets will go to the first path, and the rest will be used or sent through the second path. So this technique results in throughput increasement. Another advantage of the protocol is resilience. When one of the paths disconnected for some reason, the other paths can take over the transmission, which is a big advantage. Actually, one of the advantage of the protocol is it can go back to a normal TCP connection in case of path failure. The motivation of my research is that in the literature, multipath TCP is not optimized for IoT. And the next generation of IoT application expected to have a strict quality of service, such as high throughput and low latency. Traditional multipath TCP protocol is not able to satisfy these requirements due to some reasons. The first one is multipath TCP works independently in the transport layer. So it doesn't have any cooperation with other layers. The second one is that the routing of multipath TCP has many limitations, such as suffering from high number of transmission. This problem needs to be addressed. Actually, it is addressed in contribution number 2, and the first reason was addressed in contribution 1. The last reason is that multipath TCP is half duplex. It doesn't use a new technology called full duplex yet. It hasn't been implemented to the protocol. So it is an advantage to use this technology. That problem is addressed in contribution number 3. This is my publications. Because of the motivation that I have published 3 journals. I'll be giving you a little bit of the introduction, sorry, the literature review because of time frame. I'll be as brief as possible. When the committee has presented multi-path TCP, they designed or aimed or presented some goals. The first one is a multi-path TCP must improve throughput. So this is one of the goals of designing multi-path TCP. The second one is to improve resilience, and third one is to reduce congestion. The traffic should be moved from congested paths to less congested paths. These are the goals of designing when designing multi-path TCP. Let's have a look to the challenges. There are many challenges facing multi-path TCP. However, most common ones are packet reordering, packet buffer overload, delay, throughput, path diversity, heterogeneous networks. I will be focusing on delay and throughput since they are the main focus of this research. Solutions to the above, to the previous challenges include subflow scheduling, network coding, redundant packets, but those solutions triggered some limitations as well, such as complexities and complexity. Also, for example, redundant packets not suitable for applications with high bandwidth. So those solutions still have some problems. I proposed these kind of techniques to improve the protocol. Basically, I proposed cross-layer design, routing strategy, and full duplex communication. My first contribution, as I explained, is the cross-layer design. Let me go to the next slide so I can show you in a better way. Here is the meaning of cross-layer. In TCP/IP stack, each layer is independent, so it does some tasks and gives the output to the adjacent to the next layer. So it doesn't have any communication with the other layers. So they communicate in terms of input and output, but they don't know what's going inside. What's going inside the layer. But cross-layer design have different perspectives. So for example, application layer can be, the information here can be sent directly to data link layer to do some processing, and then goes back, for example, to transport layer, and then goes to, for example, physical layer to transmit the packets. So in TCP/IP, this is not allowed, but in cross-layer design, which gives an opportunity to improve the connection, this is that's why I personally consider cross-layer. However, I modeled the cross-layer design as an optimization problem. So I wanted to maximize throughput, but has to be restricted to some constraints. It's subject to these constraints. The first one is the flow rate. Flow rate has to satisfy this equation, so this inequality. The second constraint is about MAC layer. The media access control has to be in the same range of the protocol. And the last one is the delay. The delay of the communication has to be less than or equal to threshold here. So this is the problem statement. And the cross-layer design that I proposed includes transport layer, medium access layer, and network layer. So the medium access, the transport layer adjust the sending rate, communicate directly to the MAC layer. So it doesn't have to go to network layer. So transport layer communicate with MAC layer, and MAC layer communicates with network layer to perform the best route. Also, I solved the problem using duality. Duality means that if I couldn't reach a problem from one side, I could reach it or solve it from the other side. If this is positive, I can solve a problem using the negative side. As a result, I have proposed two algorithms. The first one is perfect scheduling. That means all nodes in the network contribute to the scheduling to find the best route and capacity and allocate it to the links. The second one called distributed scheduling. This is the BCT code of the algorithm. Basically, the neighborhood of the nodes that are close to each other take over the scheduling, not the whole networks. And here the network setting, I've got 6 ad hoc IoT wireless nodes. And this is the parameter of the experiment. I have 2 flows, A to F and B to E. These nodes are self-configured, so they are ad hoc wireless networks. E assumed to be connected to the internet via sync node. And here is the results. I compared the time versus the normalized source rate. Basically, I've got here 2 other protocols to compare my protocol with. And 2 flows, as I said, if you have a look here, I have 2 flows. So the red line and the blue line is the proposed method. The other methods close to each other, and we can find that the proposed method outperform the existing schemes in terms of normalized source rates for both flows, BE and AF. So the red one here and the yellow one always is the has higher throughput than others. Here I compared the same protocols with respect to congestion price. So we achieved the lowest congestion price here. If you have a look, the same colors here, we have achieved the lowest congestion prices in the experiment. The right-hand side here is the delay. Always, as we have a delay constraint in the optimization problem, we take care of how much delay we have before transmission. So the experiment achieved the lowest delay here for the first flow, and the second flow here also achieved the lowest latency. This experiment is for algorithm 1 in fixed channels. The same scenario here, fixed channels, but the performance is of algorithm 2 is also presented here. Same results, higher source rate, lower congestion price, and lower delay. The second scenario in the same contribution is time varying channels. So the difference between time varying channel and fixed channel is that the channel doesn't change over time. The capacity of the links doesn't change. The network condition doesn't change. That's for the fixed channels. But in time varying channels, the channels can be good, bad, or any other situation. So the capacity changes, the network condition changes, packet loss changes. So this has been taken into consideration. And this is the results of algorithm 1. I achieved a little bit, the other protocols achieved higher source rates, as you can see here, the green lines. But if you go to the this graph, you can see that the green line here has higher congestion price, and also here has higher delay. So instead of having a higher source rate instead of delay, I will take an acceptable amount of source rate, but I achieve lower lower delay. So this is the explanation of this graph. For the same scenario, we have the second algorithm. You can see you might notice that the source rate here a little bit lower than the first experiment, because the distribution scheduling usually includes the neighbors, not the whole network. So the source rate here gets a little bit lower than the other. Again, here we have acceptable amount of source rates, and we achieved lower congestion price compared to the other protocols, and also a lower latency. The second contribution is about what we call opportunistic routing. This is not a traditional routing. It's a new method of routing. This algorithm uses broadcasting nature of wireless networks to perform the forwarding. It chooses the node that is closest to the destination to be as a forwarder. So if we have a look to this network, this is a comparison between OR and traditional routing. In traditional routing, we have, if we want to send the packet from S to D, from the source to destination, we might go to this route, S, A, B, D. But in opportunistic routing, S can broadcast the packet, and any node can receive it. Any of those nodes can receive the packet. Let's suppose that B has received the packet. So instead of going this way, the packet the route can be S, B, and then go to D. The same scenario could happen to A. So basically, the difference between traditional routing is that traditional routing predefined the paths before transmission. So it has to select the path of routing before transmitting data, or even before forwarding the packets. So, but OR, the path or the forwarder selected will be selected at the transmission time. This is the difference between those two techniques. Here is another example. If we have source has some packets to transmit, and here the destination, neighborhoods will be, the packet will be broadcasted to the neighborhoods. One of the nodes will receive the packet, forward it using the same techniques until the packet reaches the destination. Benefits of OR OR has many benefits, but for the sake of because the time slot is not actually enough, I summarize it here. Efficient utilization of network resources, increased delivery rate, and decreased number of transmission. This is the common benefits of OR. Here is my algorithm. Basically, the source will transmit the packet. If the packet is received by any nodes, stop the transmission, and the source will receive an acknowledgement. Then the adjacent nodes will communicate with each other to define who will transmit the packets. This procedure continues until the packet reaches the destination. The destination will broadcast an acknowledgement so that everyone, if they have the same packet, they will try to drop any nodes receive the broadcasted acknowledgement will drop the packet. So this is save bandwidth. System model. I have this IoT network. Source is the source, and D is the destination. S is installed with a camera to detect DHL cars. So when these cars approach the gate, the sensing data will be sent over the network to the destination D. D will take over, will take a decision by whether open the gate or not. by actually sending some information to the source. The network is wireless sensor networks. The number of nodes is 10 nodes. The source and destination has two access to two Wi-Fi interfaces. So they are multipath TCP enabled. This is the simulation parameters, and the results is here. I compared the number of useful packets received in the x-axis versus the total number of transmissions. Number of transmission basically means how many number is the packet is transmitted or retransmitted. So if I have one packet and I wanted to send it to the destination, if I transmit it one time, if this is successful transmission, then the number of transmission will be 1. But if I send it and for some reason packet is lost, then I have to retransmit it. So in this case, the number of transmissions will be 2 instead of 1. So on the left-hand side, these are the existing protocols, TCP, multipath TCP, and another 2 flavors of multipath TCP. Those are existing protocols in the literature without actually implementing my algorithm. These are the existing protocols. I compared those protocols, as I said, with respect to the number of packets and number of transmission. And when we have a look to the right-hand side, after implementing opportunistic routing, we have gained a lot of, the number of transmission reduced compared to the existing protocol. For example, let's have a look to the multipath TCP in the blue line here, was about 6,400 times achieved in this experiment. But on the right-hand side, we have about 5,500. So there is an improvement, an obvious improvement when we apply opportunistic routing, specifically the algorithm that I have presented, results in reduction of number of transmission. And as a consequences, reduction of number of transmission results in reduction in delay. So I have compared the existing protocols with respect to end-to-end delay and number of received packets. So you can see here the difference. The end-to-end delay has been decreased compared to the existing protocols. I also have shown an improvement when we apply the OR to the existing protocols, and then I compare the protocols that I have used with each other, taking into account startup delay and energy consumption. You can see here, the worst case always is TCP because it's a single path, but the other 3 are similar to each other. However, the best one is this one, the opportunistic routing using redundant multipath TCP. And the same case here in energy consumption. Okay, let's go to the third contribution. The third contribution, as I explained earlier, is about using full duplex communication in multipath TCP. This piece of research investigates the feasibility of full duplex in multipath TCP. Also, the research, and I have proposed a new protocol, a new multipath TCP protocol using the same, the technology that I have talked about for duplex. This protocol called FDMP, the protocol utilizes the full duplex communication transmission and sensing feature and modified the multipath TCP scheduler. So we proposed a new scheduler for multipath TCP and also a new congestion algorithm. Reliability and latency performance is the focus of this piece of research. On the left-hand side here in this graph, you'll see this is multipath TCP, how it works. We have this number of packets, let's say from 1 to 5, from 4 to 9. 4 packets has been given to the first path, and the second one, the second or the left packets 5 and 7 given to the second path. This is the multipath procedure, but on the right-hand side, we have the duplex communication. We have half duplex and full duplex. Half duplex means that either I send or receive. I cannot receive and send at the same time. So this is half duplex. Basically, multipath TCP is half duplex. It's not full duplex. So full duplex, as I said, you can send and receive at the same time. This is the illustration of the full duplex communication. This is one hint. Full duplex communication is not actually implemented here, I mean, in practice. It is still in theory. However, most research uses this technique to improve their protocols. Here is my system model. I considered Internet of Vehicles communication system. I assume that the cars here is enabled with full duplex communication feature, sensing and transmission. I have here also 2 paths, specifically 5G and 4G. And also, this is basically the VUE, means the vehicle user equipment. So basically the vehicles. So as I said, I considered Internet of Vehicles network in this piece of research. All networks, all nodes are equipped with full duplex communication system. The vehicles assume to have unlimited energy. Also, I assume that the full duplex is used in the system, and it's based on probability. I have 3 probabilities, the terminologies here. Detection probability, the probability that the vehicle or the base station correctly finds the channel busy. That's the definition of this terminology. And misdetection probability means that the probability that the vehicle finds the channel free where it's actually busy. False alarm probability, it is the probability that the vehicle falsely finds the channel busy where it's actually free. This is the protocol. The objective is to reduce latency while maintaining the connection reliability, multipath transmission scenario. I have included 3 layers here: transport layer, MAC layer, and physical layer. The decision made in transport layer, but also based on MAC and physical layer. So this decision or transmission, congestion control, everything is in the transport layer. However, the decision here is based on some information from the lower layers. The protocol differs from the other protocols, which takes in which the packet is acknowledged at the sender side instead of the remote side. We want to reduce latency, so we don't want to wait for an acknowledgement from the receiver side, because this is actually one of the limitations of TCP protocols, including multipath TCP. So we want to improve the protocol by making the acknowledgement at the sender side based on a collision. If there is any collision, this is congestion signal. If any collision, if the network has faced any collision, that means congestion. Other signals, we don't consider it. So this is the main difference of this protocol. I mean, this is the difference between our protocol and the other protocol proposed in the literature. The protocol has the feature of congestion control, retransmission, and path selection. I'll be explaining the algorithm. Here is some features of the protocol. We have no connection establishment latency. We have no acknowledgement latency. We have reduced the transmission, retransmission time that occurs by triggering the negative acknowledgement. We have also no timeout latency. Once we detected collision, the protocol sends the channel. If there is any collision, then that means congestion. So we don't need to wait for a timeout as TCP does. So these are some features of the protocol. Here is the algorithm. Basically, when a packet is generated, we switch between 5G and 4G paths, but 5G is the first choice. If the 5G path is busy, then we switch to 4G. If 4G is busy, then we switch to 5G. So between those two paths until we find a free connection. And then when we have a free connection, we transmit and sense at the same time using full duplex communication. As I said to you, if we have collision, that means we have congestion. If we have no collision, that means that the transmission is successful and in the protocol. However, if we have collision, we perform two procedures. The first one is switching between 4G and 5G, and the second one is performing what we call back-off mechanism. So we trying to make randomness, random switching and random back-off time. This helps the protocol to address any latency. Going to the results, before the results, this is the network setting and parameters. This is the slide of results. On the left-hand side, this graph, I compared what I call SIS, self-interference suppression factor, means how much interference we got after implementing interference cancellation. So I apply the method of cancellation, interference cancellation. After doing this procedure, how much cancellation I got. Sometimes I got more, sometimes I get zero. It depends on some circumstances. But here is the measurement: self-interference suppression factor versus latency. I have two scenarios here: 20 milliseconds of packet generation interval and 100 milliseconds. Excuse me. So those results, just because of the metrics here, 120, but they are the same. I mean, in terms of protocol. The red line is the proposed protocol. The blue line is the multipath TCP, existing multipath TCP. We can see here that when we have more interference, results in more latency. Here in this experiment, my protocol works fine until 30% of self-interference factor. After this point, the protocol performance is going to be degraded. So this is the best or the maximum point that the protocol can be working fine here. But you can see here that it's going up. The more self-interference factor, the more interference I have, the more latency I get. But if you look to the multipath TCP, nearly stable here. This is because the existing protocol is half duplex. It doesn't have interference. Full duplex has the problem of interference. But in this case, 30% is can be achieved in the literature. It's an improvement. 30% is an improvement. This is for, I mean, we can look to the left-hand side, the right-hand side. The same metric here is considered, but with what we call packet delivery ratio. This is can be considered as throughput. Here, as again, in some cases the protocol goes down. In some cases, you know, I have two cases here as similar to the previous figure. I have 60 vehicles per kilometers and 100 vehicles per kilometer. This is two scenarios, a density of vehicles, and the same, probably similar results here. Multipath TCP doesn't change here. I mean, change can be stable because the effective of interference. Full duplex suffers from interference, but we achieved good results here. 13% is a good results here. 10% in terms of 120 vehicles is acceptable. I also compared the protocol in terms of Internet of Vehicles density. This is how many cars in a kilometer, and with respect to latency as well. The result is shown here for the same two scenarios, 100 milliseconds and 220 milliseconds. And we can see here the more density we have, the more vehicles we have in a kilometer affects the latency. So the latency goes up for both protocols. So here, nothing to do with the interference. On the right-hand side, we have also the same metric, but with respect to PDR, packet delivery ratio. Here is, I found interesting results here, and I will be explaining that. You can see that our protocol works probably like acceptable level here before these points. But if you can have a look here, you can see that multipath TCP goes down. The more density we have, multipath TCP performance goes down. But the proposed protocol is a little bit stable here. It's going down, but not as bad as multipath TCP. So that the reason of this performance is that we have probability, and we switch between the paths. We have 4G and 5G, but multipath TCP doesn't switch between the paths. It uses most two or more paths at the same time. So the reason of this performance can be said is that congestion control algorithm. The congestion control algorithm of multipath TCP results in this performance, while our congestion control algorithm, as I said, based on probability and also switch between the paths, finds the connection, solve the congestion signal quickly, quicker than multipath TCP. If you remember, I said that we have considered the collision as a congestion signal. So when we detect it at the sender side, we stop the transmission and switch between the paths. So we deal with congestion faster than multipath TCP. This is the conclusion slide, limitation and future work. I can conclude that a multipath TCP improves significantly, specifically delay and throughput. This dissertation proves that. Also, this dissertation informed that multipath TCP now is ready to use in IoT wireless networks. The research have some limitations. One of them is that I considered all the paths of multipath TCP in the sender and receiver sides similar. So in real life, example, it doesn't have to be similar. It doesn't have to be exactly the same. If I have 2 paths, you could have more than that. But in my research, I considered both the sender and receiver having identical number of paths. Second limitation is, apart from the third contribution, I have considered small-scale networks. It should be considered as, this is actually a limitation of my research. So the last 2 limitations is that, the time. Sorry, I will be quick. 4G and 5G is used in this research. It should be, I mean, I didn't consider any other networks. Mathematical formulation and simulation is only considered in this network, in this research. So this is some of the limitation of my research. Future work, I'll try to consider the number of paths as an optimization constraint in the future to optimize multipath TCP. Examine multipath TCP in dense networks, use machine learning network slicing, and investigate multipath TCP in new wireless networks such as 6G and 7G. The last future work is that could be, this research can be implemented in real life examples. So practical implementation considered as a future work. Thank you very much for your listening, and I hope you enjoyed this seminar. Any question?
Thank you so much, Dr. Mohammed, for this wonderful and informative presentation. Right now, we will open the questions. If you have any question, first of all, I just have a quick question about your second contribution. When you mentioned like the wireless sensor network, when you did your study, did you like try to consider like the power consumption issue with this type of network? Thank you.
Let me go to the second contribution.
I think you passed it already. When you have the DHL, you said that you will have wireless sensor network. Yeah, this one.
Yeah. Here is the, your question is about power consumption, isn't it?
Yeah.
Yeah, I consider power consumption here. You have to this is the result of power consumption, I mean, energy cost in dBm. So it's, it can be a little bit higher than usual because I considered video. If you remember, as I explained here, we need to identify or detect the DHL car here. So the source node installed with camera. So we need a video and you know, pictures in this scenario. So yes, I did consider.
Thank you so much, Doctor. So the questions are open. Please, if you have any question, go ahead.
Thank you so much, Dr. Rahman, Dr. Mohammed, and if you allow me to talk. I don't have any question actually, but I just want to say congratulations, Dr. Mohammed, for this amazing, mashallah, PhD work, and it was a wonderful and informative presentation. I really enjoyed this topic, and inshallah, we'll see more, inshallah. We can see it, inshallah, in the future, in the real life, inshallah. Thank you so much, and wish you all the best, inshallah.
Thank you very much, Dr. Hani, and thank you very much. Yes, inshallah, we'll be try to implement this research in the real life, inshallah. Thank you very much.
Thank you, Dr. Hani. Thank you, Dr. Mohammed. Please, if you have any question, we still have like probably 5 minutes.
Thank you so much, Dr. Mani and Dr. Mohammed. This was really interesting topic. I just have one question about security aspects. Not sure, Dr. Mohammed, if you have considered any security aspects in research, whether in the protocols or any of the implementations.
Thank you very much, Dr. Yusuf. Actually, I haven't considered security. It's actually, out of scope of my research. But to be honest, this point can be considered as a future work, because security is one of the fundamental things in networking. So yeah, I aim to consider it in the future, probably in next couple of months. Yes, thank you.
Thanks, Dr. Mohammed.
Thank you, Dr. Yusuf. Thank you, Dr. Mohammed. So please, if you have any question. Any questions? Okay, if there is no question, then I would like to say again, congratulations, Dr. Mohammed, and thank you for this wonderful presentation. And we'll come back. We are looking forward to see this like study implemented in the next few months, inshallah, or in 1 year. And again, congratulations. Thank you so much for all of you guys, and I wish you best of luck.
Thank you very much, Dr. Mana, and thank you very much for the audience who are attending this seminar, and hopefully I can see you in person. Thank you very much.
Thank you, Dr. Mohammed.
Assalamu alaikum.